Hi there, I hope you are well. Thanks for being here for this special season of Sharing Global Views, a show we started last year in the middle of July. We humbly appreciate professionals and thought leaders around the globe joining us and sharing their knowledge and ideas during this year and the year ahead. Hopefully, we may, to some extent, shine a light on the path toward global recovery. Also, please feel free to share your ideas with us via social media. Until what's new for today.
Very good, Helena. Thank you so much. As all we may know that we actually having designed this program in a time that we can say morning tea for the Americans, and also for Europeans that we probably have our lunch and our lunch tea. And finally, we have our more on the Asian zone that we probably have dinner. So that's actually the time we can really have a tea talk. It's casual, but actually we share a view, very different part of the world and different kind of the view from the around the globe. And today, really, we want to go even deeper to look into where we were talking a lot on the pandemic. But before we really go into more detail, please allow me to welcome our main host of our show, President host Maria Figueres, who is also the standing chairman of the GLACE. Hello, President. How are you?
Hello, Keith. Thank you so much for your kind words, and thank you so much, Elena, for being with us. Friends from around the planet, thank you so much for joining us for yet another edition of Sharing Global Views. This series of conversations are brought to you by GLACE, the Global Alliance for the Sharing Economy, a nonprofit, nonpartisan organization whose aim it is to promote the concepts, the philosophy, the ethos of a sharing economy in a planet where, fortunately, population is increasing and the planet remains the same size with the same resources. We believe that the way forward is to find business models and opportunities for investment and entrepreneurs where we can share a lot more the resources and everything that we need in our life on this planet, and therefore become much more aware of our environment and the limits of our planetary limits as we go forward. This morning, we are very honored and very pleased to have with us Professor Joseph Penninger, who comes to us from Estonia, where he presently is. I must say almost on a stop, because he is always visiting different parts of the world in the line of his work. And the topic will be ACE2 from discovery to the heart of a pandemic. Professor Penninger is the director of the Life Science Institute at the University of British Columbia, where he is, of course, also a professor in the Department of Medical Genetics. He is the research chair in functional genetics at the same university. He is also a guest professor of the Medical University in Vienna and an adjunct full professor in immunology of the University of Toronto. Professor Penninger, thank you so much for being with us here to share your work on this very relevant and interesting subject. The floor is yours.
Yeah, thank you so much for the introduction. Let me see if I can share my screen here.
We can see your screen now.
Yeah, perfect. So thank you so much. Welcome everybody in whatever time zone you are. So I'm in Europe. I mostly work in Canada, but I still have a little laboratory in Vienna. So So actually today I would tell you and would like to tell you about how we co-discovered ACE2 and how this actually became the heart of the pandemic, the COVID-19 pandemic. And at the end, maybe give you some good news that there might be a universal medicines on its way, which actually might help in addition to vaccines to stem this pandemic, which of course had this incredible impact on human lives, our social fabric, and of course all the economies, and of course also how we work together. And I think as already mentioned in the great introduction, we really have to work together. And if COVID-19 has shown us something, then it's that we all live on this one little planet. And the least we can do is be nice to each other and actually help each other. And together, I think we really have ways to solve very critical issues which affect our planet, from pandemics to climate change and many other things. Since I've been working in Vienna for a long time, I'm a trained medical doctor, then went to Canada, worked for 13 years in Toronto. I'm still professor at the University of Toronto, moved them back to Europe to start an institute, and we worked there for 16 years. It basically became the largest Howard Hughes Max Planck-like institute in Central Europe. I'm very proud of. And of course, being in Vienna, you're exposed to amazing art, not just music, but also visual arts. And one of my favorite painters is always Oskar Kokoschka. And when Kokoschka was a young man, he would paint portraits, and you only paid if you liked it. So when Kokoschka painted Auguste Forel, the family actually gave back the painting to Kokoschka. And of course, Kokoschka was very disappointed and then asked, so why do you give the painting back to me? It's a great painting. The family actually said, because he really doesn't look like our father, Forel. You see, Kokoschka painted him with the hand hanging down. So Kokoschka actually painted Auguste Forel having a stroke. But he actually didn't have the stroke. But the artist actually could anticipate what happens in the future. And half a year later, Auguste Forel had exactly this stroke. So nowadays in medicine, we would call it transient ischemic episode, so you can already anticipate something. But for me, this was always a lesson, what we should actually do using our technology, some of the amazing technology of reading genes, changing genes, human stem cell technologies, to fundamentally understand disease, to fundamentally understand how biology and physiology works and what happens if there's disease. And based on this fundamental understanding, to develop really new measures of therapy. And of course, this is critical in a planet which might go to 10 billion people, where with an aging population, that we really figure this out, how this works. Otherwise, we will be in huge political and economic and social trouble. Just a disclosure. So these are the institutions who gave me money. I also will show you some data from 2 companies I started. So in my free time, I start biotech. So that's my little fun I have, besides running a research institute and my research lab. Just that you can put it all into context. I think it's always important to know where I come from and who actually gives me the money to do this. So this is my new place. I'm now the head of the largest life sciences institute in Canada at the University of British Columbia. And actually I have my first in science. It's quite interesting because I actually go from one job to the next. So very unsecure life. So it's my first secure job in my life, having aged in the system, which is also interesting. And I also keep a little laboratory in Vienna. And if you look here carefully into the harbor of Vancouver, this is the future parking spot for my boat. So let's hope this actually works out. I actually have a grand vision for this place. So I want to actually start the global institution for biological resilience, climate change, there are pandemics, there are lots of things we have to address, aging. However, nature is amazing because it's not that something happens and we get disease. Nature is resilient, and I think it's time for science to change the narrative, how amazing this is. And we can actually learn from environments to disease, and from bacterial colonies in the Polynesian islands, we might learn how to actually handle the next pandemic. And so this I would really like to do, and maybe some of you can actually help me on this. So really tell the story of life in a positive way. And of course, learn along the way how we could actually deal with adaptation to climate change. Actually, recently I gave a lecture in San Francisco, how we could actually develop technologies to adapt life to the mass. So just some of the things we do, just try to think out of the box. Beyond this, I was involved, for instance, I'm actually a genetic engineer. So we made some of the first genetically modified animals already 30 years ago. One of which, for instance, contributed to the development of cancer immunotherapies, which of course changed how we treat cancer. Another one of the work we did was we identified the master gene for bone loss, which became now a drug used in tens of millions of people with bone loss, actually giving revenue to the company I worked for at that time, biotech in the US. It's the major drug, so they're making $5 billion a year revenue on my little discovery. I also want to mention this because biotech will be clearly the dominant industry of this century and the next following centuries, most likely. And we are just at the surface. To support biotech and these new technologies, I think makes a lot of economic sense because we can also attempt to solve some critical issues in the world. So to my story on ACE2, after my lengthy introduction. So in now already 23 years ago, I was interested in the development of fly hearts, among all things. So this is actually a fly, and here's a beating heart. And we wanted to know the genes which regulate, how fly hearts develop. And one of the genes we actually cloned and identified, a postdoc of myself who now works in Boston, was a gene we called angiotensin converting enzyme number 2, ACE2. And it's in evolution, very ancient. It actually goes back all the way to bacteria. So this is hundreds of millions of years of evolution, always maintained a structure. I should also mention my lab was not the first to report the sequence. We had the sequence, but as a functional genetic engineer, we always wanted to know what ACE2 is actually doing in the living organism. Actually, ACE2 sticks out on the surface of cells. So here's the structure of it, and sits on the cell surface and then does its trick. And the trick it does with the work we published first, again now 19 years ago in Nature, was ACE2 fundamentally regulates a system which we call renin-angiotensin system. So this system in our body regulates some of the most fundamental functions we have. Regulation of blood pressure, for instance, how our heart works, how our kidney works. Again, millions of people actually get ACE inhibitors. So by using, these are basically the master genes which regulate your blood pressure. So after my lecture, if you get up off your chair, the reason why you don't collapse is because this system actually changes the pressure in your blood vessels, and so this is why you don't faint. So this is what we discovered, this fundamental role in regulating blood pressure, kidney function, and so on. Something we call the renin-angiotensin system. And then we realized ACE2 sits actually in the lungs, which didn't make any sense. And to study the function in the lung, actually, again, 20 years ago, we built the first intensive care units for mice. So it took us many years to actually do this. And the reason was because in these intensive care units for mice, we could actually study and do the genetics and find the essential genes which regulate lung failure. And of course, lung failure is one of the because now with COVID-19, this is what kills people. So we had started this many, many years ago to study this. And turns out ACE2 protects against lung failure. So the function of ACE2 was actually, when we genetically mutate animals, is to keep our lungs healthy if there's injury. So this is where we started to work. We were laboring away in our little laboratory in Toronto and in Vienna. Nobody really cared about our work. And then this little virus came to the world, the SARS coronavirus. So the SARS coronavirus, as far as we know, came to the world in October 2002, and we had it under control around July 2003. And let's see, maybe I can stop this, otherwise. So 10 months. Within this 10 months, as far as we know, 8,000 people were infected, 8,000. Of which around 800 died. So the idea that COVID-19 might stop fast, with more than 200 million people infected, you have to put this in relation. It took 10 months for an infection, which actually infected only around 8,000 people, and it was not very infectious. Toronto, where I used to work at this time, was actually the epicenter of the SARS outbreak. One of my students was infected. But the infection was very difficult to infect one person to the other. So we could, at the end of the day, trace every infection to the first case in Toronto. So this is how we could actually contain it. And of course, with COVID-19, this new virus is much more infectious. And the many people who are asymptomatic and can pass on the virus. So that's also why it's so difficult to contain it. But it was very interesting also back then, how a little virus completely changed the social and economic life of Toronto. At this time, Toronto was one of the centers for the movie industry. X-Men, the first X-Men movie was, for instance, made in Toronto. And because of the virus, the whole industry broke down. So this was really an early reminder how little virus infections can change our life. And the reason why and then it turned out, let me see, then it turned out this ACE2 is actually the essential, and this is why this whole story developed. ACE2 is actually the central entry gate for the SARS virus. And we actually published the first paper that without ACE2, there's no infection. So basically the virus needs a target, a landing site, a door to infect us. And the door for the SARS virus is ACE2. No ACE2, no infection. So this is what we published and reported. So this was the first lab which did this. And the other thing is, we believe the reason why the SARS virus became a killer virus is because it did not only use ACE2 to infect us at the essential entry gate, but ACE2 actually protects our lungs from more severe injury, as I showed you. So basically, this virus is much more dangerous than flu virus or other viruses because it actually uses a door to infect us. And this door has a double function to protect our lungs and actually other tissues. And that's why we believe this virus became a killer. It's not just using the door to infect us and that's it, but also this mechanism of infection contributes to more severe disease. So we were laboring away to develop a medicine based on this, using a soluble form of ACE2 to treat lung failure. And the reason we did this, because lung failure is not just in COVID, it actually happens in bioterrorism, in anthrax, smallpox, the Spanish flu infection, global outbreaks of flu, and many other conditions, pneumonias and so on. So at the end of these conditions, there's lung failure, and we actually wanted to develop ACE2 for this. So I even won prizes at this time, beautiful molecular explanation why the SARS virus became a killer, a first demonstration that ACE2 is the critical receptor for the SARS virus, or the gate for the virus to infect us. And then, of course, everybody was smiling and said, it's beautiful research, but it's totally irrelevant because there is no SARS virus. So who cares what you guys did and published? And then, of course, this little virus came into the world, SARS coronavirus 2. Number 2, because it's the sibling of the first SARS coronavirus. And based on the work we have been doing, and of course many other laboratories, it was immediately clear that ACE2 must be also a critical entry gate for the SARS coronavirus number 2. So, and one of the reasons why the world could act so fast is, of course, because many laboratories over the last 20 years made the groundwork for this fundamental understanding, and so we could just latch on and act much, much faster in understanding of the disease. So this is actually how it looks. So this is the spike protein, so you all know this. This is the spike which stands out of the virus. So this is how it actually looks in real structure. And this is ACE2. So this is the famous binding site where the virus binds to ACE2. And if this binding happens, then the virus can enter our cells. And we have actually now genetic data, which are not published yet, that no ACE2, no infection. So again, ACE2 is the critical gate for the SARS coronavirus to infect us. And for instance, we did some little fun experiments. So this is a single spike, so you can actually see dancing of the spike protein, how it binds to protein. So this is where research is going, single molecule analyze. So to get back to my story. So ACE2 is the essential entry gate for SARS-CoV-2 virus. We know ACE2 protects against lung failure. And we initially discovered it actually regulating heart function. And this essential system regulates our blood pressure. So if this is real, then the drug we had been developing for 10 years and not many people cared about could be actually a drug which could be used to block the virus infection. And this is one of the important slides. So if you, so these are the two viruses, SARS coronavirus and SARS coronavirus 2. These are the spikes. It binds to ACE2. And this binding allows the virus to enter our cells and infect us. And in our cells, when it's infecting us, then it does its trick. It makes more virus. The immune system gets turned on. The whole, there's damage of the tissue. And eventually this leads to the diseases we call SARS, severe acute respiratory syndrome, severe lung failure, and COVID-19, coronavirus disease 2019. And this is, of course, the idea of therapy. So if you have a soluble form of ACE2, it's like a sponge. It catches the virus away from finding its real receptor. And by doing so, it cannot infect the real cells anymore. And of course, this should improve disease. So is this real? Actually, every single vaccine which is being developed does exactly this, to stimulate our immune system, to block this interaction. So the spike cannot bind to ACE2 anymore. So this principle is basically validated in more than 1 billion people now, because in every person where the vaccine works, this is exactly what happens. We vaccinate so that our immune system makes antibodies which block this interaction here. Also, many medicines, which actually nearly all the medicines which are approved for COVID-19 do exactly this. The antibody cocktails of Eli Lilly, of Regeneron. So the Regeneron cocktail President Trump got when he got COVID. And at very high dose, it was experimental, but that's probably what might have saved more severe disease, because they block binding of spike to ACE2. So this is basically ACE2 literally has become at the heart of essentially all the vaccine designs. And of course, a lot of drug developments which have been successful, as we know. So I think this is beyond discussion that this is critical for the understanding the pandemic. So what did we do? So this is actually how the virus really looks. So this is the virus we use. This is an electron microscopy. So if you ever wondered how the virus actually looks in electron microscopy. The other thing we do tissue engineering. So we actually take stem cells, grow out of human stem cell a little kidney. This is a little kidney. And then we infect them. We can infect them, and ACE2 blocks it. So it really works. The other thing I like to do is these are blood vessels. So I grow blood vessels of stem cells. So I'm not just a genetic engineer. So we do now massive tissue engineering. So to grow little human brains, human guts, human hearts, human blood vessels. And I believe this one day might, we are not there yet, but one day this really could allow us to make totally new medicines, replace blood vessels in diabetic disease. There are 450 million diabetics out there, understand brain disease. And we used it actually to model COVID and use this for COVID infection. So back to ACE2. ACE2 sits in our noses, in our throat. So if we would actually meet in person, and I would, have active COVID-19 virus infection, and I would speak very loudly and maybe sing even parts of my lecture, the virus would probably reach you even in the last row, having some aerosols. And this is where the virus would land, on ACE2 in your nose and your throat. Most people might never realize it. These are the asymptomatic cases. Some people might get a common cold, a little fever, a little cough, that's it. However, if the virus gets access to the lung, ACE2 sits very deep in the lung cells. And this is why people get a very typical pneumonia, which is very different from flu pneumonia. You can even hear it, a COVID cough is very different from a cough somebody has if there are other types of pneumonia, because it's very deep. The reason it's very deep is because this is where the gate is. This is where the landing site of the virus is. This is where ACE2 is. And then, of course, massive inflammation starts. Lung disease starts, lung inflammation. Virus is produced. The virus gets into the bloodstream. And ACE2, the gate of the virus, again, sits in the heart, sits in the brain, sits in the kidney, sits on the blood vessel, sits in the gut. And this is why COVID-19, when it starts, it's a lung disease. However, in severe cases, it's actually not a lung disease. It's a multi-organ disease affecting the brain, the kidney, the heart. People get diarrhea. Most people actually died because of blood clots, because it affects directly the blood vessels. So, of course, there's a lot of things going on. The immune system gets going, how our blood cells coagulate changes. However, ACE2, being the essential gate the virus needs to infect ourselves, explains where it lands, explains the severity of pneumonia, explains the spreading into other tissues. And so we actually develop a medicine based on this. As I told you, this is the name, how it's called. In our little biotech, I named Pyron Biologics. It's basically ACE2 soluble form to catch away the virus from finding the real door. And the reason why we do this is twofold. It reduces the virus infection, like a vaccine, like the antibodies being developed and have been approved. For instance, the European Union, I think, just announced 400 million euros to buy antibodies, which are still under development of GlaxoSmithKline to do this. So this is what this is doing. And I explained to you why we think this is actually critical. And secondly, it should protect tissues from damage. And we actually finished a phase 2 clinical study on not enough patients, unfortunately, in severe COVID-19. And we are going now in the US in a platform trial called Connects to expand this. One thing we are facing, actually as a little biotech in Europe, is unfortunately we don't have access to trial sites in different countries. For instance, where there's a lot of COVID at the moment. Indonesia, Vietnam, other countries, South America, Central America. And this is a real problem for us. And if you really look which medicines have been developed, it's basically always the same, and it's always the same from the big companies. Because the support for really innovative medicines was lacking. And so I think one message I would convey is, would be really great to set up a system where really innovative medicines, which makes sense. I showed you, this is the principle for all the vaccines. This makes real sense to do this. Can also be developed and maybe tested in places where we as a small biotech don't have access to infrastructures or access to the patients. And because we are developing medicine for everybody on the planet, not just for a select group of rich people in Europe. The other thing, of course, which turns out now is that 30% approximately of people who had SARS-CoV-2 infections and even mild COVID have long-term symptoms, brain fog, they cannot remember well, heart conditions, kidney conditions. So COVID is not, you have the infection, and then some it's hardly anything, and some it's more severe, and then it's over. So it appears there are long-term effects, which of course makes sense if you think about this, because if the virus can get access via the gate ACE2 to the heart, to the kidney, to the brain, of course it can lead to some damage, which then can be propagated even months later. And of course, there's also autoimmunity, so overstimulation of the immune system. But I think this is something we have to face now, and for probably many, many years. So, and variants. So we all know there's this unprecedented development of vaccines. Because the people were developing other therapies, so the new spike, the new ACE2 could just pop it into their nanoparticles and moved it very fast. Of course, with a massive support from governments, and that's why all was developed so fast. Unfortunately, therapies, and this is my second message I would like to say, is therapies are lagging behind because the governmental and institutional support was by far much less than the support for vaccines. It's absolutely clear that we and the governments and the international institutions had to support vaccines, but the variants tell us the vaccines might not be the solution to COVID-19. So yesterday, Israel released the data. I think from 9 million people in Israel, 5.3 million have been fully vaccinated. So the twice full vaccination protects against severe disease by 90%, which is great, but still 1 out of 10 people get sick. And it only protects around 39%, so that's the Israeli data, from being infected, meaning, if I am now in the room with you and I cough at you and you have all been twice vaccinated, probably 6 of you might actually get infected, 6 out of 10, most likely with the Delta variant as we know it. Delta, which is now spreading all over the globe, it's more infectious, it makes more severe disease, it's more lethal. Also makes sense because everybody who has the infection is an evolutionary incubator. In every person where there's a virus infection, there are billions of viruses produced. They make little errors. This is basically evolution at the global scale. So there are variants, there are many variants out there, many of which actually they're not in the media, but I know about them. And there will be new variants coming because of the system, how it works. Delta emerged, as far as we can tell, last November. It took around 8 months to reach Europe and other countries. So probably the variant we will have in winter is incubating somewhere in a place we are not aware yet. So this is happening. So of course, in this global scenario, we have vaccines, we have antibodies. Science has made a major contribution to control the pandemic. And of course, the people who do vaccines will now make a vaccine against the Delta variant. And people who make antibodies will make antibodies against the next variant. However, there's actually one medicine which should work against all of them. And this is ACE2. And I'm not just saying this because I discovered it. It's because the virus cannot mutate itself out of ACE2. Because if it mutates itself out of binding to ACE2, there will be no COVID-19 disease anymore, because ACE2 is the landing site in the nose, in the lung, in other tissues. So we actually have a potential universal medicine against all variants, even variants which might emerge in 5 years. And therefore, I believe in this entire scenario we have now, with the health measures and close downs and wearing masks, which of course essential, having vaccines, having new medicines. It's critical to develop medicines where we believe they could work against all variants. Because the next variant, and we all know it, and I don't need to convince you because you know this anyway, is just at the verge to exploding somewhere. I know in the US, for instance, the Lambda variant is just gaining steam. So does this really work? You know, I'm just telling you something which is nice science, nice utopia, but can this actually really work? You know, there are many people who have grand ideas, but at the end of the day, we should show that make something work. And so if I'm a scientist, I have to show you some data. So this was the initial virus, and actually we had a Swedish isolate. This is what we published in a paper in Cell. So this is the medicine we're developing, human recombinant soluble ACE2. So we needed this amount of this protein, soluble form, 25 microgram, to block around 50% of the infection. So this is the South African variant, which is called now Beta, much more infectious. And you see the same amount of this protein here, which we have developed for therapy, nearly blocks the infection totally. And this is the British variant, now called Alpha, and it nearly blocks the infection totally. And this makes complete sense, because these variants have emerged to be more infectious. And why are they more infectious? Because they bind better to ACE2. So the Delta variant is so dangerous, for instance, and also these other variants, because normally, if I cough at you, maybe 10,000 viruses need to stick to your nose to get you infected. With this variant, 100 of the viruses might be already sufficient. So you can imagine how this works. And the reason why you now need only 100 is simple, because they bind better to the door it needs to enter our body. And of course, if you use the door, then you can block it better because it binds better. So it's a self-fulfilling argument, but it was important to show that it actually works. The other thing is we're actually working now on some inhalation together with people at NIH and National Cancer Institute and people in Toronto at the University of Toronto. So basically the idea is, so, imagine we now meet and I have COVID, I cough at you. So what do you do afterwards? So, knowing now if I have Delta, 6 out of 10 of you will get actually infected again. So how can we protect ourselves? And of course, one idea would be, there's certainly other ideas out there, but one idea would be, let's just inhale this universal medicine. So everybody can get an inhalation of ACE2. This should block the virus and it should reduce the people who actually get infected. It's the door, it blocks it. And it doesn't matter what variant I had, and I might have coughed at you. So this is basically where we are. So the bottom line is that actually science has delivered. All the investments in science, in crazy science, as I showed you, we worked on fly hearts, panned out because it made a contribution to understand the pandemic and react very fast with vaccines, antibodies. So we have amazing technologies to in our arsenal. However, it's very important that we work together and and really leverage these technologies. And there are also ideas out there and drugs out there, as I showed you, which could be really used to develop as a pan-COVID therapy, universal therapy. And there are many other viruses out there, by the way, which can bind to ACE2, which might jump into humans in the future. So this could also really work in global preparedness for the next pandemic. Even don't know which virus might jump, but this particular group of viruses use ACE2, so we have it already in our fridges. And if the next pandemic hit, we might be able to do something. But this also means we should really rethink, this whole business model, because no institutional investor is investing in global preparedness. Because I have been there, I asked people to help me before the pandemic hit, and everybody knew something will happen, but they were all into, and also for good reasons, into making fast money, buy the next house, sell it, invest in AI, invest in internet and in the Googles of this world, which makes a lot of sense because they're driving our economies, and of course the returns are much faster. So biotech return, especially something where we say this could help against the new outbreak, is very different. So that's why I think we should really fundamentally think how this can be done, how this can be financed, because biotech to develop this is not cheap, as you can imagine. Also, for instance, I started another company. We have this amazing new technology where we can find the weak spots for viruses, SARS virus, Zika, flu virus, Ebola. So the idea is to develop totally new disruptive medicines. And we can do it, but again, we have to really adjust the business model. Actually, for this, the European Union is funding us, which is nice, at least in a larger network where I put together people who grow human tissues from stem cells, who do Ebola infections, who develop new technologies to address this. So my point is it can be done. We have technologies. I can promise we can do it, but we have technologies to attempt to better understand this and of course be ready for the next one. So, and with this, so this was basically my little story on ACE2, how we discovered it, how it became the center of the pandemic, how fast the system responded to make drugs and of course vaccines which block the ACE2 spike virus infection. And I also strongly believe, being in this for many years now, and I love viruses. It's my life. This is, I find them totally fascinating. And I also strongly believe that by this fundamental understanding, it needs a gate, and we can actually manufacture this gate, and whatever variant comes, we could block it. That there are really attempts we could develop for global preparedness and have medicines, in these intervals where new vaccines need to be developed, new antibodies need to be developed, which actually can also protect us from getting more disease or being even infected by inhalation. And there are many people who contributed to this so that I'm allowed to stand in front of you, even if it's only via Zoom. And science, and please allow me to say, for me, there's a reason I became a scientist, not just because I was nosy and wanted to figure out things, because I strongly believe science is actually the best peace project on the planet. We have problem, and we all think about this problem, and together we might be able to solve it. And it totally doesn't matter how we look, what color our skin is, what we believe in, because this is an equal playground where we can think about important issues of our world and make the world a little better. So that's why I believe to support the sciences all the way is actually one of the best projects we can do on the planet to keep the peace and make a better life. So thanks for listening.
Professor Penninger, thank you for a most amazing, outstanding conversation. It not only amazing and outstanding, but also inspirational. Because if there's one thing that we need in the world today, it is to maintain hope and the illusion that we will get past this, and that science, as you have described it here, the most interesting peace project that we could ever have, will be able to solve some of these complex issues that we're dealing with. To hear you take us from the study of ACE2 in the heart of flies to the determination over years of hard and intensive work that ACE2 is both a regulator of many of the systems of our body, but also the gateway for these infections. It has a double role, is a fascinating story. Now, if I may ask you, Professor, please, I'm sure we have tons of questions and limited time, but when you discuss soluble ACE2 as a possible therapy, because it would avoid the virus from entering the ACE2 that we have in our bodies, it would cling on to the soluble ACE2. How far away are we from that?
Our phase 2 studies have been finished. So the message is we need a larger study. So we need to have recruit more patients, which we're trying to do now in the US in the Connect study, which is actually supported by the US government and the NIH. But it would be great if we could also roll out this study in countries which are much more affected at the moment, also with more severe disease. And that's really where we are massively limited. We don't have the connections, we don't have the money to actually do this. The other thing for the inhalation of phase 2, we also work with colleagues in Europe, Canada, and the US. We are basically ready in September to do phase 1 clinical studies, healthy volunteers, where we can test this just to make sure everything else is already ready to move forward. And it would be great if, for instance, the regulatory people allow us to do this very fast, so we can actually move this very fast into people actually really exposed to the virus. Frontline workers, people have been early exposed to the virus. So we are ready to move. If we, again, the limit is, it's always the same. The limit is, have enough access to infrastructures, have teams on the ground which can go actually where we need to go. And of course, this costs money. And that's why I want to be frank, that's why we were unfortunately much too slow for my own taste.
Thank you, Professor. T, let me turn it over to you. Do we have questions from the audience?
Yes, sir. Dear professors, thank you. I just, before asking this question, really want to say that you really bring another dimension for us to see, because we're talking about sharing economy a lot, but without this point of view, you mentioned that the global, you really need to think of a way to start to not just working on the current economy to share it, but also need to prevent our future problem. If the economy able to work towards that, it will actually prevent us from many problems, same as what we always talking about the global, global warming and others. So, thank you so much for bringing that aspect. and very inspirational. Now we have this question here. What are the challenges during the drug development that you have encountered? Because we believe you already developed a drug, polio, which has been used successfully against osteoporosis. So please give us some feedback on that. Challenges.
Oh, yeah, polio, when I was a young scientist, I did all this genetics, and we did the genetics on the master gene for bone loss. And actually this big US biotech took and developed it also over 10 years, but they got the approval, I think, 2010. We first discovered it and published this in 1999. So it took 11 years, but they had the money and the people and the cloud to move forward. And I think they're now the largest biotech on the planet, was 120, 130 billion. So that's, so there's a lot of money in this, but it takes a long time, and many drugs die along the way because, side effects, one never knows. And so it's not an easy business, but of course, at the end of the day, if it works, can really make the lives of people better, and of course can have a massive economic impact. As one also sees in BioNTech, what they did to their stocks, having the vaccine, and Moderna. Actually, one of my friends in Boston is one of the 3 founders of Moderna. And they developed the Moderna because they wanted to deliver RNA into the heart for heart failure. And so this is actually where they came from. And I think last week they were worth more than 100 billion. So they're smiling. And in Vancouver, where I work now, in terms of economic impact, there's a little company called Abcellera. They developed the first antibody which was approved for COVID therapy. That's the Eli Lilly antibody. So Eli Lilly took this up. And with this, Abcellera actually was riding onto the stock market on the Nasdaq and did the largest IPO in Canadian history. So a company, a little small company in Vancouver with 50 people working, was all of a sudden worth 17 billion. And I can tell you they're hiring all our best students now, because they're paying 3 times the salaries we can pay in academia. But it's another, example. And I think there will be many more examples because the world is, we grow older, there are lots of issues we have to deal with. And so I think this is just the surface we are facing in terms of success stories, and of course also in terms of, economic impact.
Yeah, thank you so much, Professor. Thank you so much. You surely bring this biotechnology science really on top of our mind. That's really critically important and great impact. And thank you so much for the answer.
Yeah, but I can also understand, because I talk to many investors, that they're also a little shy to invest because, it's complex, it's complicated, it's, it might take 5, 6, 10 years to see some return. And so I can also understand, that it's not such an easy, it's not just, hooray, let's do this. There are also other considerations one must take.
Thank you, Professor. We have many other questions. Time is running out. I think we have time for one more question. Alexander?
You're muted still. So.
Alexander, I think you're muted.
Thank you, Mr. President, and thank you, Professor Penninger, for this exciting lecture. And hello from Austria. I think the investors should know a little bit more about your work, and beside your academic work, you're also involved in several biotech companies in Austria and also in China. So what is the respective corporate purpose of those companies? Are you working on novel technologies? So the world should know.
Yes, the first company I showed you, ACE2, development of ACE2, that's called a Piron Biologics. So they're already, a more mature company. So, and they also have a cancer project. So one idea is to actually do cell cancer therapy by the bedside. to do it fast. Somebody's tumor, you actually take out blood, activate immune cells and reinfuse them and you go home. So to enhance the chance of survival in cancer therapies. So that's what we're doing. My new companies, we have this amazing technology. We can actually play evolution. You know, many processes took millions of years of evolution. We can actually do these processes now in one afternoon. So we can basically play evolution in one afternoon and allow evolution to design better drugs and figure out how drugs work. So that's why we also work with this company in China, because there's this amazing wealth of Chinese medicine where they know something works, but in many cases they have no idea why they work. But of course, so this is where we come in. I think we have technologies to figure out why they work. And of course, if we know why they work, then it opens up you know, the whole global market. So that's what we're doing there, and it looks relatively promising. And that's also why I'm learning from China how they invest. You know, the biggest biotech hub in the planet is Boston, and the second biggest biotech hub is Suzhou outside of Shanghai. And so they're very interesting business models how to do this. And actually, I always sometimes, since we are talking, you know, in this forum and want the world work together, sometimes I find it interesting because, you know, when I say I work with Chinese, then some of the Americans say, oh, this is not good, you know, we don't want to have anything to do with you because it's China. But Jesus, you know, we have one planet, you know, we have one health. You know, at the end of the day, we should all work together. If this is in US or Europe or China, to find solutions. So this would be one of my wishes. At the end of the day, you know, I mean, as we know from COVID, there are no borders, doesn't care, you know, where I pay my taxes. Might help, you know, at the end, if I get faster vaccines and medicines, as we unfortunately learned, but at the end, there are no borders for disease. In my third company, which I started, where we got some first investment from a Canadian biotech, is actually we developed how to make perfect human blood vessels, and we want to really make a complete disruptive new therapy to give people who have bad blood vessels healthy blood vessels back, based on tissue engineering and blood vessel engineering. As I said, there are 450 million people out there with diabetes. The main problem of diabetes, why people turn blind, the kidneys fail, organs fail, is because the blood vessels, why the wounds don't heal. So our grand vision is to use advanced human tissue engineering to give healthy blood vessels back to patients. You know, people who have shooting wounds, apparently they heal very badly. So the people with deep burns where the wounds don't heal, but we can actually use our blood vessels for wound healing and so on. So completely disruptive long term. So that's what we're up to, what I'm up to at the moment. Because some other ideas in my head, but you know, it always takes a little time from the idea to incubate, find people who support this and get it onto the ground.
Thank you very much. I'm sure that a lot of people heard those words now, and they want to be a part of a healthier world. So let's hope for that. Thank you very much.
Thank you, Professor Penninger. I want to recognize ex-Chancellor Feynman, who is here with us. Werner, thank you for joining us on this most interesting lecture. And you may want to add some words or comments. I think you're on mute. Okay, well, in any case, we recognize you and thank you. Professor Penninger, thank you for a most interesting journey. I have to say that in the series of our lectures, we have had outstanding speakers. You have increased the bar by a huge amount, by an order of magnitudes, with respect to future speakers on this series of sharing global views. Fascinating the way you started out with a story of art, Kokoschka, and how you transitioned into how we can use technology to look into the future of medicine, or of illnesses, and how we can solve many of the challenges we may face in the future. You tell a story of life, and you tell a story of life in a very optimistic and upbeat way, and that is what we need in the world of today. I loved your calling science the greatest and most important peace project that we have on this planet, and your constant reminder that we all need to work together. Thank you ever so much, Professor Penninger. It has been an absolute privilege and inspiration to hear you, and we thank you for your participation. Friends, thank you ever so much, and we will see you 2 weeks from today on another Sharing Global Views conversation. Have a great day.
Thank you for the invitation, and thank you that I got to know you all. Bye.
Thank you all.
Thank
Bye-bye.
you.
Bye-bye.
everyone.
Thank you very much. I'm really grateful. Thank you very much.
Thank you,
Oh,
Werner.
that's
Thank
Chancellor
you.
Berman. Thank you.